Merci. Thank you. I'm going to switch, sorry, to English because there are non-French speakers in the room. So that's going to be easy for everyone. But don't worry. With my accent, you're French people. You will understand me. And even if, like, Mistral is a fierté française, as we like to call it, now, like, Mistral is known way beyond the French border. So I think it's also a nice way of, like, putting things in place. So the first thing I want to do is, so to understand who we are and what we do, we have to rewind like exactly 3 months before today. I received an email from one of the organizers about basically giving a talk here. And I was like, okay, cool. We have something cooking. It was like at the end of the training of Mistral 12B. And I was like, okay, this is going to be easy. I'm going to talk about multimodal. The first thing to understand with Mistral is that we like to ship things and we like to ship a lot. So this is basically what happened. We released more than one model, obviously. We released also a bunch of new features on our platform, and 30 minutes is definitely not going to cut it to introduce all of the new things. So I'm going to focus on 2, let's say, main topics for this last presentation, which are multimodal and edge computing / agents. Fortunately, a lot of things have already been said by many of the previous talented speakers, so this is actually an opportunity for me to go faster. But I hope that you've been paying attention, because I will assume that you've watched all of the previous slides, and I will not go back on some of the technical details. First is multimodal. So this you already know, from text to more than text, obviously. I'm going to focus on one specific type of multimodality, which is text or image to text, which is interesting because that's the natural extension of what you can do once you want to cross this first border of like just doing text to text. What do you have in books besides text? Images. That's basically the simplest, let's say, way to think about that. And what people are looking for is basically a way to interact with documents that contain not just text, but also images to solve these 3 main categories of problems, which are image captioning, where you want to be able to basically describe an image. That's the easy one. You notch things up a bit. You land on OCR, optical character recognition, where you want to be able to extract text information that is basically visually embedded within your image. And last but not least, you have visual question answering, which is about extracting semantic information from the image. Spoiler alert, this is not new. There were models that were doing that long before the era of generative AI, but those models were specialized in one of those tasks. The idea here is to basically replicate the, let's say, the workflow that people started to like and love with LLMs, which is being able to do many things at once with a single model and using nothing more than natural language as the interface. That's what we aimed at doing. So back in September, we decided to open source and gift to the community our first multimodal model, which is called Mistral 12B. In pure Mistral tradition, we released first a single tweet that contained this torrent link to the model weights. And 1 week later, we released the blog post about, well, describing what the model is and how it basically differentiated from the rest. So it's a 12B model. It's small-ish. It does contain a vision encoder that has 400 parameters. It does support arbitrarily sized images and interleaving text and the images as well, a large context, and it's licensed Apache 2. That was the first step. Step number 2 was done a few weeks ago, where we introduced our second model called Mistral Large, and we said, yeah, the first step was nice. Now we have to be a bit more serious. We multiplied the size of the multimodal decoder by 10. We multiplied the size of the vision encoder by 2. and we reach fairly interesting performances, as you will see later on. So before talking about performances themselves, I also wanted to highlight the fact that, as we have discussed today, you can have biases when basically looking at the performances of a model. And when you look at how an LLM is evaluated, it's important to understand that it will always be important to go beyond basic academic benchmarks. So, for example, when you look at purely text-to-text models, and you want to compare performances, you will use things like MMLU, for example. The idea is to say that with MMLU, you're going to basically submit the model to an MCQ test about generic things in terms of knowledge, in terms of reasoning and whatnot. And then the ability of this model to answer to those MCQs is going to basically derive a score in the form of the accuracy in a multi-class classification problem. But for images, that's not enough, because we have something new now, which is the, well, image and text and semantic meaning embedded in that. So you have specific things to evaluate multimodal models. For example, this one called MMMU, where it's basically the same approach. You have an MCQ test, but this time you have an image in the input. And it's not like simple things like, do you see a bird, do you see a dog, do you see whatever in here? Like, take a look at the lower right one. You basically have to compute the value of like the difference of potential in the electrical circuit that contains a transistor. This means that the model must know about basic electrical engineering. It must know how to basically understand that what it's looking at is an electric circuit, and then it should know how to basically derive the computation. This is the level of test that we are looking at. Another test more specific to VQA is basically how to properly extract semantic meaning from an image. Again, you don't want things like, do I see a dog, do I see a cat? You want more. Is the door open? Is the door closed? Is the cat wearing a leash? And if so, which color is it? This is the level of detail that you want to extract semantically meaning from the images. But those are all well-known benchmarks, and it may be a bit difficult to reproduce those results because evals are complicated to re-implement from scratch. So we did a few other things besides just reusing the model. We actually created our own benchmark. We open sourced the dataset. We created our own library of evals. We open sourced the library for full transparency so that people can really and easily reproduce the results that we published in our paper. We took the inspiration in terms of workflow from the empty bench eval. And if you want to try it out, please do, because we always welcome additional numbers using this MMMT benchmark to compare it with our models. So in terms of performances, the 12B was doing pretty well, but for me, the interesting part is this one, where with Mistral Large, we actually managed to get on par with Claude 3.5 Sonnet and with GPT-4o, as well as with the biggest Gemini 1.5. So this is basically where you get after a bit more than 1 year on working things at Mistral. Now we're going to dive a bit deeper into how things work. I'm not going to re-explain everything here because this is part of a slide that was shown previously. But there are a few differences. Remember that when you're doing multimodal, you're going first through this encoding step, but here there are a few more nuances. First, as you can see, there are additional tokens when you encode an image before the projecting step. And this is typically to account for images of various ratios. You don't want to limit yourself to square images. So you introduce special tokens that are able to break down an image into a sequence of rows. And each row is represented by a list of 16 by 16 pixel patches. And then you have also an additional special token that basically represents the end of the image itself. So that at the end of the day, you are able to generate a sequence that blends images, text, and those images will be of basically any shape. You're not limited to squared shapes. If we zoom even further on the encoder architecture, you've heard about CLIP today. we were not super happy with clips. We basically decided to re-implement our own, and we retrained it from scratch. That resulted in a 400 million parameter for the 12B 400 million parameter encoder. With a few tricks, we diverged a tiny bit from the vision transformer paper. We moved from absolute positional encoding to relative position encoding. Very simply put, when you embed the information inside vectors from your tokens, you also want to add the information on where that token is inside your sequence. You can do that in an absolute fashion. You can do that relatively to the other tokens. And the idea with relative positional embedding, and here more precisely with rotary position embedding, is to basically reuse the work that was done for text for what is called ROPE, so rotary positional encoding in one dimension, and extend that to 2 dimensions. There was a very, very interesting paper on that. And then, like a few other tricks, another interesting one is what we call sequence packing, where when you flatten the images, you also want to compute things more efficiently, so you're going to concatenate all the images, but to retain their position, you're going to add a block diagonal filter or mask at the attention step. All of that is nicely detailed in a paper where we basically put the main results for 12B, and where we also retained our magnificent graphical design. That was the first half. Now we're going to change the topic a bit and talk about smaller models. Why is mini the new big? We've talked about agents today, but there was a topic that was not that much discussed, which is edge computing. Well, it was discussed, in fact. Not everybody has like tons of GPUs at their disposal. People also want data privacy, not just at, let's say, the network level, but sometimes at the device level. They're like, the data that is entered on the device should never leave the device. It should not go on the private network. It should never go on the internet. And with that, so smaller things also comes with constraints, but people also expect more. It's kind of a paradox, but smaller things also mean that people will expect things to be snappier, faster, and when it comes to agentic workflows, what comes next after like thinking about agent is understanding how to call the different actions that are made available to this agent. And this is what we like to call tool use or function calling. And you need a model that is good at that. So we looked into the topic, and we released 2 small models, Mistral 3B and Mistral 8B, and in good French, un Mistral, des Ministraux, hence the jeu de mots. So those models were basically built for using fast inference. They are 128K long as well. They were specifically trained not just to be good at the basic task that everybody expects from an LLM today. We also extended the multilingual abilities of the previous models to those small ones. We specifically also trained them to be very good at function calling. And since now the old and venerable Mistral 7B that you probably know is more than 1 year old, 2023 is very far away in the timescale of LLM. So we also encourage people to retire the old 7B now, because it is kind of subpar in terms of performance compared to the latest and greatest ones. So we also encourage them to switch to either 3B or 8B, because those are way better in terms of performance. Why small, and what are the challenges? When you want to shrink things, especially when it comes to LLMs, you have to consider 2 things. The first one is memory. Transformers are memory bound in the sense that when you basically run something like inference, you have a given amount of memory, you load the model's weight that is going to eat part of the memory that you have at your disposal, and then as the inference process goes, you're going to fill something that is called the KV cache. The KV cache is basically a smart way to avoid recomputing the key and value tensors that are required when you compute the famous attention score that is required basically to understand which best token is going to be predicted next in your sequence. And this KV cache grows, obviously, with the sequence length. And at some point, for a sequence that becomes too long, you end up like well, you're not going to have enough memory for sequences that are too long. So you're like, OK, I will need bigger memory. But remember that we're going to also go smaller in terms of devices. And to compare between the memory that you have available on one H100 versus something that fits in your pocket, like a phone, for example, you see like the ratio on the right. So you have to come up with a few tricks. Trick number one, quantization. It's getting late, but yes, sorry, I'm going to speak about that because it's important. The underlying concept is actually fairly simple. The idea is to say that information is important. You want to retain as much information as possible while reducing the amount of memory that you're going to take to represent that information. In the world of computer science, it means representing a given number in less ones and zeros than the original format. So what you do is basically scale down the set of numbers you have in your tensors by basically first calibrating the scale factors, applying those scale factors, and you can go from something like FP32 to represent floating points to something like int8 or even int4 to represent numbers only as integers within a small fixed range. And since those are integers, you obviously also have to round the results and then perform your operations. And naturally, you descale at the end, at the output of your block, your layer, to get the results. This is one thing that you can do after training a model that's called post-training quantization, but this obviously is going to degrade the accuracy of the model. So the solution is actually to add something more on top, which is called quantization-aware training. The idea is when you train the model to also account for the fact that the model should minimize quantization errors. And to do that, inside your, let's say, your training loop, you're also going to add more steps in the form of quantization and dequantization steps, so that the resulting model is, let's say, more robust to quantization at the end. And it is so robust that if you take a look at the results of the sweep that was done on the right here, we can actually get something that is close to almost lossless compression, meaning that we have a result here where we did some kind of like a hybrid quantization where we quantized the weights into int4 and the KV cache into int8. And we actually managed to retain almost full precision compared to the non-quantized version, which is pretty nice. So the cherry on top is that we took QAT, we basically implemented our own proprietary stack on top of QAT, where we actually mix different levels of quantization, depending on whether you're looking at the weights, at the KV cache, at a given block, at a given channel. And this stack basically allows us also to derive the resulting model regardless of the target architecture. Because the goal of edge computing is really to deploy your model on the edge on smaller devices that have specialized hardware. And this is also why, within the context of Les Ministros, we signed a partnership with Qualcomm not so long ago, so that we are able to work with them to deploy our models on edge and have them work out of the box with their Snapdragon processors. The second aspect for those small models is about agentic workflows. I'm not going to spend too much time on this one, but the problem is that if you've been working with agents, you know that this is extremely, let's say, token hungry, in the sense that when you have to define the list of functions, this is going to require a lot of tokens. When you retrieve the outputs of the function calls, it can also be super verbose. So you need to find a way, even if the model is super small, to account for that and to keep a big enough context window. So for that, we applied a trick that is called interleaved sliding windows. And simply put, it's a way to basically, for a given token at different time, not just look at all of the past token, but recursively look at a sliding window so that at the end of the sequence, in a way, you have full visibility over the past. All of this is described in detail in another talk that my colleague Pierre did at .ai a few weeks ago. So if you want more details, because this was basically just scratching the surface, don't hesitate to watch his talk. It is available online. So one of the previous talk was about, I don't know, living dangerously and whatever. So I'm going to do a demo as well, because it's the end of the day. And sometimes it's also nice to come back to simple and fun things. So for the demo, I'm not going to talk about like quantization and whatnot. We're going to go back to something a bit more like down to earth, and we're going to use le chat. Who knows about le chat? All right, no need for introductions then. That's perfect. So who knows what le chat can do? I'm going to show you like a few examples. I don't have much time left, but with my remaining time, I'm going to show you, I think, enough for you to be curious and to test things out on your way home, hopefully. So Christmas is coming, and I assume that you're all going to meet friends and families, and usually what happens is that someone says we should do Secret Santa. How do you do that? Maybe you have a WhatsApp family group and you ask about who's going to participate and whatnot. But if you want to be, let's say, a bit more hype, you're going to say, OK, I'm going to create a cool web app that does that for everyone. Problem is, if I don't know how to write, I don't know, HTML and whatnot, it's kind of a pain. So I'm going to open le chat. I'm going to ask it to write me a Secret Santa web app. And I'm going to here enable this thing called Canvas. What does this do? So yes, it's giving me some code, but also a bit more. It's actually giving me the code of the application, which is looking good so far. So if I want to inspect the results, I can do something like this. And I can actually generate pairs, like if I type Alice, and then if I type Bob. So I'm not going to type for too long, obviously. All right. So ideally, you see the idea, but if you don't want to stop there, you can do things like, for example, I don't know, put that in red, for example, like this. And like you can progressively iterate on this thing so that you can like either that or well, like the possibilities are basically endless. But here the idea with this Canvas feature is to basically allow people to experiment and get feedback results live. What else can we do? So as you may have guessed, I am French with the accent. So if, for example, I'm asking this model, oh, all right, not available anymore. It's OK. We're going to use something else. I'm going to stick to English then. And so you're going to your friends and family's parties, and you're going to have to bring something to eat or to drink. So you can ask something like this, generate an image of the perfect dessert for a Christmas party. Practicing my one-hand typing. So this is, hopefully, so I'm not a big fan of those like 3 dots, but this is hopefully going to generate an image. We talked about multimodality earlier. In Lusha, we actually added the ability to not just ingest text and output text, but we can now also output images. We've been partnering with people at Black Forest Labs for this. So this is basically their API that we're calling under the hood. So this is looking nice, but now, if I'm in Paris, where can I buy this? And this is going to introduce the third and last feature that hopefully I will be able to introduce to you. We talked a lot about agents. The idea of agents is to act, but also to leverage external resources. So the third and last feature in Lusha that I wanted to show you is native web search. So you are able now to actually ask Lusha for information that can be retrieved from the internet. And image generation, canvas, web search, this is available for everyone for free today. And the underlying model is our best model, aka Mistral Large. And as you can see, like the last message was actually not just web search, but now that the image is generated, you can also do multimodal input and take this image as an input for the subsequent, let's say, rest of the conversation. This is what we like to call the beginning. We plan to add much more than that for a more enterprise-ready version of Lusha. And we also aim at exposing all of that programmatically for developers. So as of today, the API of Mistral is available here and there in the clouds and on our own platform. And yes, if you want to join the fun, because we're going fast, but we always like to think that we're never fast enough, so we still plan to accelerate and release more models, more features on the platform. If you want to join the fun, you're more than welcome, because we are hiring. So on that note, thanks for attending, and we can open the floor for questions.
Bon, parce qu'on ne peut pas finir sans prendre la dernière question de la journée. On va prendre une seule question pour Mistral.
Alors, tout d'abord, merci pour la présentation. Et je voulais rebondir sur une des parties que vous avez données, en particulier sur la partie où vous avez dit que vous avez changé la partie du clip parce que vous n'aimiez pas trop et donc vous avez créé le vôtre. Et donc vous avez lancé récemment un code astral en utilisant l'architecture Mamba. Et je voulais savoir si vous pensez que cette architecture elle va pouvoir être scale à des modèles un petit peu plus gros que 7 milliards de paramètres.
Okay, so I'm going to answer in English. So does Mamba 2 scale? So do we plan to scale Mamba 2 up to more than 7 billion parameters? So the Mamba 2 model that we released was basically the result of an internal research project. Right now, most of our work, as you have seen on the releases, has been on like dense transformers. The idea of a Mamba model is to remain small. That's the thing, because their architecture is basically built for fast inference. So 7B is a nice. No more batteries in the mic? Ah, yeah, cool. So we don't have specific plans to scale it up. I think we're still waiting for feedback from the community, because one of the reasons why we open sourced the model was also to get feedback from the community on how it was used and where did they see like performance issues and whatnot. We're still waiting on having enough feedback to iterate on that front.